Very good evening to all. Myself, J. Umar Mohammed, Assistant Professor, Department of Mechanical Engineering from Tyagaraja College of Engineering, Madurai. First, we start the section with a welcome address. First of all, very good evening to all of you and warm greeting on behalf of Management, Principal, Head of Department of Mechanical Engineering. Today, we have a chief guest for our this webinar session on virtual manufacturing is Mr. Pradeep Navalpakam, founder and principal consultant, Honey Home Consultant, Chennai. It gives me immense pleasure in warm welcome our chief guest, Mr. Pradeep. We welcome you, sir. Our consultant, Mr. Pradeep, has 20 years of industrial experience across design, manufacturing, operation. He has worked extensively with the US, Germany, and China. He has implemented projects on a global scale. We have also have another resource person, Mr. Rohit S. Mallaya, Head Emerging Technology, PLM Indus Technology, Bangalore. We also welcome him, sir. Next, I would like to give a warm welcome to our beloved college registrar as well as Head of Department of Mechanical Engineering, Dr. K. Chokalingam, sir. Then I like to give a warm welcome to all deans, faculty members, and students of TCE for this wonderful webinar. Finally, I like to give a warm welcome to all HODs, faculty members, and students of various other engineering college in and around Tamil Nadu, like Government College of Engineering, Tirunelveli, PSG College of Technology, Coimbatore, Velamar Engineering College, Madurai, PSR Engineering College, Sivasi, Bannariamman, the Institute of Technology, Satyamangalam, Savita Engineering College, Wales University, Anna University, Madurai, St. Peter Institute of Higher Education and Research, and St. Peter College of Engineering and Technology, Commerce College of Engineering and Technology, Madurai, National Engineering College, Kovilpatti, Srinivasan Engineering College, Karpam Institute of Technology, Coimbatore, Bharathasan University, Sri Ramakrishna Institute of Technology, IMT College of Engineering, Noida, Ramco Institute of Technology, AAA College of Engineering, Sivasi SCAD College of Engineering and Technology. We also have the participants from many polytechnic like Government Polytechnic, Nizamabad, PSR Polytechnic College, Mohammed Sadek Polytechnic College, Lakshmi Ambal Polytechnic College. Once again, I extend my hearty welcome to all of you for this webinar session. Thank you, everybody. Now I invite our college registrar and head of Department of Mechanical Engineering, Dr. K. Chakalingam sir, to give felicitation of this. Sir, Chakalingam sir, over to Chakalingam sir.
Thank you, Umar. Thank you for your welcome address. Is it audible, Umar?
Yes, sir. It should be slightly, your volume should be, you have to increase your volume, sir.
Increase my volume.
Raise your voice, sir.
Yes,
Okay, sir. Voice is okay, sir.
Is it okay?
Okay, sir. Okay, sir. Go on.
Okay. So, good evening, everybody. The respected the chief guest of the webinar, Mr. Pratik, the founder and the principal consultant, Honey Home Consultant, Chennai, and then the another speaker, the Rohit Malaya, and my dear colleagues and the students of TCE, and the participants from other engineering college and faculty members and students. Good evening, one and all. It is very great pleasure to organize this kind of webinar to share the knowledge of processing engineers to our students, as well as update the happening what is taking place in the industry. In that way, we have arranged this particular topic, the virtual manufacturing. So, according to me, it is very important one. Even though it was this particular technology is started in 1990, due to the heavy competition among the various industries, but still it is valid and it has matured enough to address the various issues of the modern manufacturing environment. Actually, this virtual manufacturing is going to integrate the geometrical models and various engineering domains such as design, analysis, simulation, optimization of resources, and decision-making tool within the computer generated environment. Simply say, we are not going to manufacture the real. Sometimes it is okay. or most of the cases in computer generated environment, we are going to make the product, and during that manufacturing, computer environment manufacturing, what are all the difficulties we are going to face? For example, this particular virtual manufacturing is identifies the problems of production functionality and manufacturing before it occurs. So in such a way, when you are going for a new product, especially when you are going for a new product, especially in manufacturing environment, the tooling is very much important one. Whether it is a press tool or it is a punching tool or whatever it may be, whether it is correctly fitting or in assembly, and any problem is occurring or not, we must know about it before going for the actual manufacturing. We must to foresee the problem, what will happen. So in that sense, this particular virtual manufacturing gives the or helps for design for manufacturing and design for manufacturing and assembly. So with the help of the virtual manufacturing, we are able to produce a component. What are all the problems that may arise during the manufacturing actual environment? This is the basic concept of this. With the help of this virtual manufacturing, we can validate the process, we can simulate the process, manufacturing processes, as well as we validate the process. Once the process is validated, we can go for the real-time production. It is one biggest advantage when you are going for the new product development or new product manufacturing. Addition to that, this virtual manufacturing helps for training the engineers and other technicians also. In that way, without going for the real-time environment, depends upon the caliber of the technicians. He can more than one times or more than 5 times, and he can go through the simulation and he can practice it. Once if he convention with the particular processor, then he can go for the manufacturing. In that sense, it is useful for the training also. And with the help of this virtual manufacturing, we can new product can be marketed in the opt time or in the shortest time with cost effective way. This is most important, cost effective way, because in the competitive environment, everybody try to bring the solution for a particular problem. For example, you take the COVID-19 environment, everybody is trying for introducing the vaccine. Similarly, in manufacturing environment, so society faces a particular problem, all the manufacturers will try to manufacture the product and try to introduce the product at the earliest way. So in that sense, to introduce a new product at the earliest way, this virtual manufacturing is helpful to the industrialist. Because of all these advantages, the this virtual manufacturing is used in many industries. For example, heavy engineering industry, automotive industry, and then aerospace industry, food planning industry, and healthcare industry. So to identify to name a few, Ford Motor and General Motors recently they are developing the virtual prototype, not the actual prototype, physical prototype. Instead of the physical prototype, this Ford and the GM and all creating the virtual prototype and getting the opinion from the engineers, peer group, and then customers whether the product is good or not, and so on. So addition to this, Ford and GM, Hewlett Packard, IBM, Intel, John Deere, Motorola, Sony, Apple, and US Air Forces are some of the industry are using this kind of virtual manufacturing. So in the competitive environment, the virtual manufacturing is very much important. And before getting into the actual manufacturing, we will produce the component in the computer generated environment, and we can see what are the pros and cons occurring during the manufacturing. And once if it is rectified, then we will go for a real-time production in such a way that it is reducing the cost, reduce the manufacturing cost, it is reducing the product development cycle time. It reducing the it reduces the fatigue of the workers and able to train the engineers as well as the train the technicians. So in that way, this particular topic is very much useful and highly relevant in the modern manufacturing environment. So, which is Mr. Pratik has a very good experience in the virtual manufacturing. Similarly, Rohit Mallaya also having the good experience. So, their experience sharing in this webinar will be highly useful to the faculty members as well as the students of our college and other participants also. With these three words, I concluding my introduction remark and over to Umar Mohammed. Thank you, everyone.
Thank you, sir. I will start the webinar with the introduction of our chief guest, Mr. Pratik. Our chief guest, Mr. Pratik, completed his BE in Mechanical Engineering from Shanmuga Arts, Science, Technology and Research Economics during the year 1995 to 1999. He has also completed his MS in Mechanical Engineering from University of Kentucky, US during the year 2002 to 2004. He started his career as graduate engineering training in Hindustan Motor Limited, Chennai, from May 1999 to April 2000. Then he worked as a quality engineer in Caterpillar, Chennai for 2 years. After completing his post-graduation from University of Kentucky, he started working as a product development engineer in Clearwood Enterprises, Orange County, California, US. He also worked as a assistant general manager in manufacturing engineering for India Crop Solution from May 2011 to May 2012. He has had the position of project manager in India for tractor operator station John Deere Pune for more than 2 years. He also worked as a head for engineering and business development in Vesco Limited, Kolkata. He also had a position as a director of operation in Leebai, Chennai. Lastly, he worked as a plant head in SRM Technology, Chennai from July 2019 to January 2020. Finally, he officially started his own consulting company called Honeycomb Consultant in Chennai during January 2020. His company provides consulting and service that aim at solution for strategic and operational issues using an established principle of business management and lean philosophy. Moreover, he is a certified leadership coach from Neuro Leadership Group UK and helped people to achieve their potential through this coaching. With all, I'll heartfully welcome Mr. Pratik to deliver his presentation to the participants. Over to Pratik, sir.
Yeah, thank you, Mr. Umar, for the introduction. Hopefully, you can hear me.
Yes, sir. Yes, sir.
Okay. Well, first of all, I'd like to thank Tyagaraja College of Engineering for giving me this opportunity to interact with the students and share my experiences. And thanks to all the faculty and head of department. So with that, I'll directly jump into the subject. Now, the aim of today's presentation or session is to give you all an overview, a high-level overview of virtual manufacturing and its applications in the industry. And here, what I'm going to do is I'm going to start from the basic philosophies of how virtual manufacturing evolved, and then talk through some of the practical examples which I was part of during my career, where we have used all these tools. And later on, also show you a couple of interesting videos. Again, those are real-time situations which I was involved with the use of these technologies of virtual reality and augmented reality. With that, then we will go on to the question answer sessions. And after that, we'll be happy to open up a platform or introduce you to a platform where students can register and stay up to date on the latest trends in the manufacturing with respect to digital and virtual manufacturing. Okay, so here we go. So what is virtual manufacturing? Now, this is what I stated here is basically the definitions which I have understood and I have put in based on my working in this field. So it's performing activities in support of manufacturing virtually. Virtually means you're off-site. You're not physically at the location where the manufacturing happens, and you're doing it on a computer. And we know manufacturing is basically a conversion of raw material into usable form. It could be steel, it could be tubes, hoses, any other things. It is also conversion of usable raw material into finished products as per the customer specification. So these are the definitions of manufacturing which we have learned during our education. Now, virtual manufacturing basically evolved with globalization. As companies grew and started having multiple locations, and as the need for standardization grew, there became a need for having centralized manufacturing team. And along with that need, there was an evolution of the application, which basically paralleled along with the digital technology evolution. So in the initial days, there was one factory located at some local manufacturing location, and they had their own local manufacturing engineering teams doing the process design, the layouts, the line design, implementation, throughout production. So basically, it was dedicated.
Pratik, I think your slide is not changing. Currently, what I see is the virtual manufacturing slide.
Oh, is it?
Yeah.
Sir, I can see the local manufacturing slide.
It's changing, sir.
Changing, sir.
Okay. Maybe it's my side. No problem.
Okay. So, like I said earlier, with a dedicated team supporting each factory, the companies were producing. But as the need for the products went higher, as the globalization expanded, the things changed. So earlier, they had a local culture, they had a local people, it was easy to interact, they could speak the same language, and they all grew up in a similar background. Hence, the productivity, the overall outputs, the issues that came up were easy to resolve and move forward. However, upon globalization, the factories started at multiple locations, and either the suppliers were from different places or the same product was made in different locations. And there were multiple supplier sources, multiple stakeholders across the globe. So then there came into the complexity of cultural differences, languages, communication. Hence, communication became a big challenge. So companies realized the need for standardization. No matter where the product is made, it has to be made the same way. And it has to have the common parts. Only then the cost benefit is leveraged. So with this came the concept of virtual teams. Virtual teams, centralized manufacturing, design and manufacturing teams sitting virtually in an offshore technology center, supporting the multiple factories. And they were the ones driving in the standardization of process and tools, however, keeping in mind the local requirements to support the factories. And the local factories were to focus on the day-to-day work, daily production and output, production, delivery. That way, the businesses were able to leverage the best out of their investments. So this is the background of virtual manufacturing, how it evolved. And now what we see here is basically, the product development life cycle. It is again a very high level drafted one. And there may be things that I might have missed here, but whatever is of relevance for today's discussion is in here. So what you see here at a business level, companies look at a project opportunity. They look at an opportunity in the market, and then a project plan is made. Then the project is detailed, and then the implementation starts. And after that, the project is closed. So this is the high level backbone or the structure of how typically a project gets executed. Now, what we are focusing here are mainly the design and manufacturing function, because that is of interest to today's group. Now, when you look at the design, what are some of the key milestones or key activities that happen? The product specification is defined, a high-level cost is estimated, so that you look at the compliance and you look at the business case. Once the business case is established, a design concept is made. And once the design concept is made, as the design progresses into the detailing stage, there's a detailed design. Then there is a system validation and compliance test. So in earlier days, the system validation used to happen in the physical test laboratories, and physical prototypes used to be made. So this was one of the most time-consuming activities which caused a lot of delay into the introduction of the product in the market. And post that, there is the design improvement life cycle that the product goes into. What you see below here is the manufacturing life cycle. Again, going on with the same project milestones, there is a manufacturing feasibility. When a product is identified, then the companies look for feasibility for them to make it, whether they have all the required competencies and capabilities to manufacture it. And then a strategy for manufacturing, which location is best to serve the customer, which location do they have the capacity, etc., are defined. And then a factory master plan is made. So once that is done, then the engineer gets into the detailed work of designing the processes, designing the facilities, identifying the constraints of capacity, and then once that is done, they start getting into the physical builds. Okay? And once the physical builds are done, there is a design improvement cycle that the design goes into, and then the production is started. So this is kind of the overall manufacturing design cycle that you see here, and encapsulating the activities. Now, post that, it gets into a continuous improvement cycle, what we call a CI cycle, because once a product is into the market, there would be constant upgrades or changes that would be coming on, primarily driven by customer requirements or marketing or competition, and in some cases, compliance driven. So compliance driven example is the emissions. The emissions regulation forces companies to go back and make updates to their current product. So now these are all fundamentals which were earlier triggered by the QS 9000 in the olden days. And today they are part and parcel of the new product development life cycle for most companies. And these are guided by the basic quality planning principles of the what you will see APQP as part of QS 9000 and the PPAP requirements. So this is something that we all must keep in mind as we now start to talk about virtual manufacturing and how we can embrace the opportunities in that. Moving on, now we'll focus a little bit on the design cycle. So when we look at global design today, a design consists of parts. Parts go into a component, components go into a system, and systems go into a product. So this is probably the simplest version I could put forward to give the sense of complexity that exists in real-time world today. So when you look at some of the common machinery that is on the road today with agriculture or construction, there are typically about 30,000 parts that go into the machinery. So these 30,000 parts again get accumulated as components, systems, and products. So what companies do is they have their virtual engineering teams, individual design engineers designing the parts at a part level. And then there would be an integrator who would integrate it into components and systems and products. So these are today possible only with use of digital tools, like you will see in the upcoming slides. So now when we talk about a part design, I want to also mention about what is significant about part design. Okay? Although we're talking about virtual manufacturing today, it is important for us to understand the virtual engineering portion of it, which is primarily focusing on product design. Because today, design and manufacturing are not two sides of a coin. They work very closely hand in hand, as you saw in the earlier product development chart. So it is very important for us to understand the constraints and the philosophy of design as the product gets progressed in its life cycle. So when a part is designed, here the photograph that I have here is basically to give you an example. What you see here is a very simple fuel cap. Okay, this is a fuel tank cap that we all see in our cars today. So what goes into design of this cap, right? There are compliance, okay, ARAI or respective bodies, SAE, have standard guidelines and compliance safety norms to ensure that the product does not cause any legal or safety issues. So the design engineer has to work in compliance with those standards and some of the basic specifications which are there. And the specifications are derived based on the standards and the application. And then there is a geometry. Now you can see here, for example, the physical constraint for the design engineer is that it has to go and fit into the fuel tank and it has to be accessible for the end user. So there comes into the mating parts, the assembly, and the serviceability, which he has to keep in mind. Then the physical boundaries, right? You are forced to work within a physical set of constraints, boundaries which cannot change, and which will define the clearances and the tolerances within which the product part must be designed. And finally, also the material. Okay. Now, one may design in olden days, the design used to be based on the material locally available within the area where it is designed. But today, when we talk about global designs, we have to keep in mind that the common material which is available at most locations. So material availability is very important, and the cost. Okay, you will also see later today how, within virtual engineering and virtual manufacturing domain, the costing is also taken into account. So this is specific to a part design. Moving on to a component level design. Okay, so what you see here is again an example of the railway. When you go out near a railway track and see the wagons that go, so this is what is underneath the wagons. So this guides the wagon. This is just for information. So this is called a bogie, right? So the bogie is a system, and some of these elements within the bogie are components which consist of multiple parts. So when the component or a design is done at a component level, it integrates multiple parts. So it becomes very critical for a designer today to visualize the how overall the components come together, or the parts come together to form the component. So this is an example where the digital tools which we spoke yesterday of, and the virtual visualization comes into play for effectively designing the components. And when a designer who's sitting virtually and designing a part is able to understand how it fits into the next level of the component, he is able to understand the constraints better and able to churn out the design first time right. And then there is virtual validation. Okay, so virtual validation is a key part of virtual engineering, where many companies no more go into lab tests. What they do is they use the advantage of the digital technologies to do the virtual simulation. For example, if it is structural validation, we have finite element methods which are there, and today softwares are capable to handle advanced complex designs and still give you a reasonable predictable result. And similarly, if there are heat factors, for example, I know there's an example where in a tractor we had to simulate how the exhaust of a tractor comes into the cabin, or how we have to design the exhaust system such that it does not come into the cabin. So there we had to use the fluid flow analysis and the heat factor within the engine envelope to analyze that. So these are a couple of examples where virtual validation is used today. So now here is an example, a live example of how this virtual engineering, specifically finite element analysis, is used in the industry. Again, going back to the bogie example, what you see here is a typical wagon that is used for carrying iron ore. So this is a common sight for anybody who stays near the railroad lines. And this, what you see below is the bogie, which is, again, through use of virtual tools, you're able to explore the various components and understand visually. You don't need to be physically present near a bogie to understand how it falls through. And this is an example now where the finite element method was actually used not to check the structural integrity, but to derive the loading and boundary conditions for redesigning this component using composite materials. So this was for an advanced research project. This was done. And so there we simulated the existing brake beam. This is the beam that applies the brake on the wheels for the train. And the loading conditions were put in. And this pattern was used as a benchmark or as a maximum load criteria for design of the composite bogie. Okay. So what is of importance for today's engineers is to understand that in finite element methods, the person must have a good functional understanding of the system before he or she gets into it, understand the material properties, the boundary conditions, the loading, and also the interpretation of the results. Very often the results might be so evident that one may say, oh, this is already failing in this location. However, one must need to have experience and good understanding of the system to interpret the results correctly. So this is a practical example in the Indian railway system where the finite element methods were used. And I'm sharing this because I was part of this project. Another example of use of virtual engineering, again going back to the bogie, was to help optimize what we call the unsprung mass. So every time a mass within a system is not suspended directly, it is going to cause damage to the overall So the idea was to optimize the weight of the central element methods again to identify the need for some of the inner elements and optimize the same. Again, here it was also used as we had benchmarked an existing bogie to validate the loads and boundary conditions for a new bogie bolster design. Again, a practical example being used in the industry today. So we spoke about part design, we spoke about component design. So next stage in this is a system design. So when the components accumulate to form a system, when the components are integrated within a system, it's important to make sure there is a functionality check that is done. Okay, so there are several tools today in the market for performing. For example, if we take the suspension system of a two-wheeler or a four-wheeler, it is going to be complex for us to go and do manual calculations and also visualize how the system would function on the road, right? So earlier, how they used to do it is they used to have cameras embedded to understand the vertical and lateral movements and have strain gauges attached to them to understand the loading criteria. So now what's happened is with advance in the digital front, there are softwares available to perform what we call multi-body dynamics, to understand the dynamics of the interaction of different parts, what we call bodies, which interact with each other and which are constrained by each other. When a suspension system is attached to the chassis and to the axle, it is constrained at those 2 points. So when it functions, it is not allowed to freely function, but it works under constraints. So that's a simple explanation of that. But MBD assessments are very common today in the automotive field. Then the other thing that is done is clearance analysis. Again, when multiple parts to the level of 20,000 parts going into a system, and if there are 25 different engineers working on it, it's very common for people to miss out on some of the features of the part. So before the design is progressed further, there is a clearance analysis which is done to make sure that the gaps and interferences or part interferences don't exist and there are not any unpredicted gaps that are there. I'll show you some examples of that in the next few slides. And then the other one is a tolerance stack-up. What used to be a quality function before, where they used to do manual calculation of stack-up tolerances within each component. Nowadays, there are software which are capable of doing this tolerance stack-up analysis. Now, tolerance becomes important both from the functionality of the product and also from the cost of the product. The higher the tolerance, the higher the part cost. So it will be very important to balance the tolerance limits in order to deliver a profitable product at the same time functionally effective product. And the other activity apart from the functionality check is the system level design review. So what happens is once a system is designed, the companies now use virtual models to have their cross-functional teams go through a detailed verification of the design. So the design is verified for, number one, the intent, whatever is the intent of the design, number two, for manufacturability, number three, for serviceability, and so forth. So there is a detailed system level design review that is conducted as part of the product development process. So what you see here is an example of clearance analysis. Now the two products here are only for giving you a feel for what the product was. It's not the same brand, it's not the same product that is represented above. It's only to make you understand that these are common examples today which companies use these tools for. Okay, so here, this is actually a clearance analysis done on the chassis for one of the baler. What you see here is a baler product, which is used to collect bales in the farm. So when the entire chassis is designed, there are multiple parts that go into it, and the engineer performs a clearance analysis. So in this case, he realizes that the clearance of the hole and the bolt which is putting in is not sufficient. So he will go back and correct it. So before the product is made into a prototype or a physical model, these type of fundamental errors are clear. Another example that you see here is on a cotton picker, again, for the basket where there are multiple components that are welded and assembled. There is a clearance analysis that was performed where for the joints, again, the clearances between the two faces of the mating parts was high. Again, this is a practical example that where it is used in the industry today. Next, we talk about tolerance stack-up analysis. So this is, while this has been a quality function, nowadays it is falling on the plates of a manufacturing engineer and in some case a design engineer, where at the time of design itself, they go back and validate how these at a system level and at a component level, how the tolerances stack up and what is the room that they have to increase the tolerance bandwidth so that they're able to improve or reduce the overall cost. And what you see here is a typical representation. When the tolerance band is wide, the cost is lower and the yield is high. Yield means the output. The first time right is the yield. And when the tolerance band is reduced more and more, the costs become higher and the yield becomes lower. Okay? So it is very important for a designer today to ensure that the tolerances are done in a commercially viable sense, at the same time, functionally viable sense. So next, we'll see a video of how the digital tools today enable a manufacturing engineer to perform this analysis as he validates the design.
Variation in assembly build problems. In this example, we'll look at the variation introduced through the process of building an automobile brake assembly, where controlling the angular variation between the brake pads and the brake disc is critical to the proper function of the braking mechanism. The entire process model is represented in a tree structure on the left side of the window. The process tree contains all the elements that comprise the analysis: parts, assembly operations, and measurements. The features contained within each part that are used as datums in assembly operations or for measurement are tolerance using GD&T, or geometric dimensioning and tolerancing. Once the features and tolerances for all parts have been defined, assembly operations identify how these parts will assemble or interact with one another. The next step is to define the measurements for the critical dimensions to be controlled. In this case, the angle measurement between brake pad and brake disc. Once the process model is defined, simulations that replicate the virtual build of the brake assembly are run. From the reports generated, the variation magnitudes and contributors may be viewed for each measurement. Model parameters, such as tolerance values, may be changed and the simulations rerun to ascertain the impact of the change across the entire assembly.
So what we saw there was the tolerance stack-up analysis for this wheel disc assembly as it was narrated. And this is something that today, it's a very common sight. You go back and see design engineers and manufacturing engineers who use such tools. There are many tools available in the market where they are able to concurrently modify the designs and determine the adequate tolerances for the parts, thus being able to deliver a product first time right, at the same time at the right target costs. Okay. So just a second. Okay, so next we come to, so we saw part design, we saw component design, we saw system level design. Okay. So now when all of this integrates into a product, that is the end saleable commodity for which all the groups have been working towards. So it's important for the designers now to look at systems integration, how the systems integrate. So this is a very, very important and critical function that you will see in the video to come. And as they look at the integration of systems, they are able to dynamically modify the designs through digital technologies available today. Another key feature which you will see is the marketing alignment. Much earlier in the concept stage itself, companies today use virtual reality capabilities to showcase the upcoming product to their dealers and their customers, to receive live feedback so that their valuable feedback gets integrated much earlier in the product design lifecycle. Again, another video that I'll show you towards the end showcases this capability. And then the compliance check. Okay, today when a tractor is designed, when a car is designed, they have to comply to certain specifications, such as the turning radius, the overall boundary of dimensions, the emissions, etc. So these are possible, again, like I mentioned before, through use of virtual tools. And serviceability checks. Okay, once a product is designed, you don't want it to be in the field, and then now the service engineers are finding it difficult to service the vehicle. So accessibilities, the commonality of parts with its predecessor model, the comparative benchmarking, all of that, these functions are today enabled through use of virtual technology. So next we will see how a system integration is performed using digital tools. What you see is an air gun. This is actually a drill, hand drill, and or a hand screwdriver, where you can see dynamically how the designer is able to verify the individual systems and components that have been integrated. And at areas where additional clearances are required, he's able to modify them. So here you can see at the body, he's able to go and adjust the rib. Right now, at the time this part was designed, the designer might not have been aware of potential interferences. However, at the time of integration, you see such interferences come into notice, and then the integrator is effectively able to go back and make minor adjustments to the design. So it doesn't have to go back into the entire cycle of redesign again. So he is able to effectively visualize. He doesn't have to physically see the product. So now this particular change will be very interesting. After all the parts are assembled, it is realized that the height of this particular feature is not right. So he's able to go back and now modify the height of that feature and quickly correct the design. You can see how there is a misalignment. And so he's able to align, if you see there is a radius earlier where this feature was. So he's able to move the radius and quickly be able to correct the design. So this is another example of virtual manufacturing. So now what we'll see is a part cost estimation, how this is used in today's world. So the virtual tools, there are virtual costing tools that are available in the market today, which are used for effectively managing the cost of the total product. So the 3D data is taken, and then the materials are assigned. Then the cycle time of manufacturing is estimated, again virtually through the information available in the system. And then the cost per hour based on the location where it's manufactured, that is fed into the system. And then the overall manufacturing cost is able to be derived. Okay, so all the data right from the product design and the material to the factory cycle time, the overall work content of the product is now available for the engineer to go back and estimate the overall manufacturing cost. Okay, so that was the design cycle, some of the examples that we saw there, which is applicable and used day to day in today's industry. Now we move on to the manufacturing cycle. So what we call manufacturing design is basically the design of the manufacturing process. Okay, so this is the deliverables of a manufacturing engineer today as a new product gets delivered. So earlier on, he goes in and we have to do the design for manufacturing. So, so we look at part commonality so that we are not going in, like for example, fasteners. We don't want to keep on adding different varieties of fasteners as new products get developed. So we want to look at common parts that are already existing in the system and try to use the same part as much as possible. That would help reduce the cost and help reduce mistakes on the line. Next one is the product complexity. While companies focus to deliver what is important for the market, they also today have to keep an eye on the overall complexity as it would impact the overall manufacturing cost and the feasibility of manufacturing. So this is a place where the digital tools come in very handy, like you will see in the further slides to come, where an engineer is able to sit off-site from the factory and determine whether the design is feasible to make or not, and what are the changes that are needed to make it manufacturable. And he then studies it from an ergonomic and safety standpoint. Now, this is an area that is taking great significance in recent times because there is a realization that operator ergonomics significantly impacts the productivity. And then as the labor laws become more and more effective, safety of the operator becomes imperative. So it's very essential for today's manufacturing engineers to analyze any product very closely from a safety and ergonomic standpoint. And that is possible with virtual tools so that he doesn't have to wait for the physical product to be made and then go and define his tools and processes. He's able to do that virtually. The next stage is where he goes and defines the process definition as they call it, where in case of an assembly, the assembly sequence is defined. So once you know a product, once you know what are the components in the product, once you know what is the demand for the product, how many products are to be made every year, every month, every shift, then accordingly the assembly sequence is made. And the product synchronization, there's a visual representation of how the overall product would go together. And then using this, he makes his line design. So what we call as line design is how many stations are required, how many people are required. So this is where demand-based planning is very common today in industries, because earlier industries used to produce and stock and then sell. However, they end up carrying the inventory and those costs turn out to be detrimental for them. So nowadays, the industry mostly works on demand-based planning, and the manufacturing engineer has to treat this as one of the key inputs towards designing his line. And then he establishes work content and then look at the takt time and the stations. So all of this is done using digital tools and virtually offsite from the manufacturing facility. And then the tooling, the assembly toolings, the press toolings are all designed because you have the CAD model, you have visually how the product goes together, and so your tools are able to be designed accordingly. So once you have a visual representation of how the product goes together, then you're able to plan the layout. Okay? So there are tools today where you're able to replicate a factory in 3D, and you're able to replicate the virtual in the virtual environment. What is the working space available? What is the space for the material to be presented to the line? And that's how the layout designs and material flow are done today. So while these get ready, then there is a cross-functional review of electronic builds. Okay, the prototype builds are much few in number, as it was mentioned earlier during the session today. So companies opt for doing an electronic build where the prototypes are done electronically. Okay, so the entire product going together station-wise, the sequence, validation of that, the processes, the tooling, the layout, the safety, ergonomics, all of these are done using the digital tools. And also, we are able to analyze any disruption to the existing products on account of introducing new products. So one of the key factors is design for manufacturing. You will see some pictures in the next slide of some of the effective designs and some of the poor designs also. But it's important for us to understand the importance of the need for design for manufacturing. So what happens if a design is made and then the part is manufactured and then you find an issue, you have to go back and redesign it. So there is a cost impact on account of that change, because you make a part, you make a mold or a tool, you build the mold, you make the part, then you decide the mold has to go to change. So the cost of doing that is going to be higher as the product cycle progresses. So it's very important for engineers today to identify problems much earlier in the stage. So that's where the need for DFM comes in. So here specifically, we'll talk about design for manufacturing assembly. Okay, there are various DFMs. There's design for casting, there is design for manufacturing machining, there is design for paint, there is design for serviceability, etc. But what we focus on today is specifically design for manufacturing assembly. So what we mean by that is the design gets validated at a part, at a component, and at a system level for manufacturability, for assembly. So what they check is whether the assembly is feasible, whether the operator has access to the area where a part has to be assembled, where the tool has to be reached. So today the software are available for performing reach analysis virtually, then visibility analysis. Because one of the things that's detrimental towards productivity is blind operation, where the operator cannot physically see the part that he or she is assembling. So engineers today validate such things early in the design stage, and then they try to eliminate as much as possible. The other one, like we talked about ergonomics. When we say ergonomics, we're talking about reach of the operator. We're talking about the position, because there is a nominal height, working height below the shoulder level, which is the best to reduce the fatigue of an operator. Then visibility, like I mentioned, blind operations. Then the weight of the component, the posture, the movement, etc., which causes fatigue to the operator. So today, these are the designer is able to, or the manufacturing engineer is able to validate all of these through digital tools and recommend changes in the design, or if that is not possible, design alternate processes to mitigate some of these issues. The other one is the commonality and complexity which we faced. Imagine there is an assembly station where the operator has to put in 25 different fasteners. Now there's a new design which comes in, it's going to add 4 different new type of fasteners. So there is every chance that the operator will assemble the wrong fastener for the wrong product. Hence, it's very important to keep commonality in mind. So here are some pictures that you see where the virtual tools are used. All of them are different pictures, so I'll explain each of these. So what you see on the bottom left is actually a electronic assembly line. Okay, you can see how the operation is actually complex for the engineer. It is in a difficult posture for the operator to reach to a particular area, right? And in this case, you can see the operator is not able to very well see what is happening inside areas where he has to perform an operation. So typically what the engineer does today is they provide for an inclined surface for performing such operations, which they are able to validate much earlier in the process design stage itself. Next to what you see on the above left of the screen is where there is an operator who's trying to reach a part. However, in his process, he is constrained by a boundary here. So this is again something that is detrimental for his posture because he has to reach out to it. In some cases, it may be essential to have the boundary from a safety standpoint. So keeping that in mind, the manufacturing engineer has to design a tool or the process or the work table for these operations. So this is again a use of virtual tools. One is able to perform such validation. Another one that you see on the bottom right of the screen is where this operator is bending down to do an operation. Again, you can see where she has to stretch to do that operation. So when they do this, if the stretch is inevitable, unavoidable, then they will work on having lesser number of hours for this particular operator, and then they will change the operator frequently so that the fatigue doesn't come in. At least today, virtual tools enable the manufacturing engineer to identify such areas and plan for them accordingly. What you see on the top right here is a virtual cell where there are 2 robots performing a pick and place operation. And this is the level of visualization that is possible today where you're able to plan for space for forklift to bring in the part, and also study the movement and the accessibility for these robots to perform the operation, and also virtually program these robots to avoid collision. Okay. So here is an example of a poorly designed setup. Okay, these are examples again live from today's factory. What you see here is a workbench that the operators are sitting on. This is ergonomically not suitable because there's every opportunity for him to hurt the line. So this is an example where things are not planned ahead and then you just run with the flow. Here is an example where the operator has to bend down to pick up a part. Again, ergonomically not recommended at all. So today with virtual engineering, virtual tools, we are able to plan for avoiding such situation way ahead of time. And here is an example where, again, poor ergonomic posture where the machining center is being programmed with a makeshift arrangement. Okay. So now we talk about the product synchronization chart. Okay, so this is again a visual feel. This is so this is something that you would see on the highway. Such machines are common sight today. So the digital tools enable a manufacturing engineer to visually conceptualize how the product goes together. So you can see here, he's able to define that first the chassis is put in, then the fuel tanks are integrated, then the axles are put in, and then there's integration of the cabin, and then the boom assembly, and then the tires. So with such tools available today, again, the manufacturing engineer is able to sit off-site and effectively communicate with the factories and define the best way to assemble a product as they get rolled out in the market. So at the early stages of the product development itself, these are conceptualized and accordingly planned. And these help effectively communicate with the stakeholders so that any mistakes or any problems are identified much earlier in the product development lifecycle. Another key aspect in virtual manufacturing today is material presentation, how the material is presented to the line, which has a direct impact on the productivity and the safety. Apart from that, it also has an impact on the cost, because when more material is able to get shipped from a supplier to the factory, you're able to optimize the transportation cost. So these are examples where you see the material handling systems are used, are designed using the digital tools today. And the plan for every part is made before the part is physically produced. Okay? So it's important for the manufacturing engineer to ensure that he presents the right part to ensure quality of the product, in the right quantity to control the inventory, and the right orientation to define the productivity. Another example where virtual engineering is used for supporting manufacturing activities. This is actually a non-conventional area where the paint system, when parts are fed into the paint system, the parts are loaded on the load bars. So conventionally, the orientation of the parts are designed only after the part is made. However, through virtual tools today, we are able to do that effectively and define the labor costs involved in loading the parts for paint, and also ensure that the parts are oriented the right way so that there is optimal use of paint. At the same time, the paint quality is also controlled. Another aspect is the product shipping, where the end product is shipped, where companies today make the product at one country and export it to another country. And there are local rules in the destination country where local assembly is mandated. So this was a project that was executed in such a scenario. This is a representative product, not the exact product. So this product being shipped in a 40-foot container, and how virtual or how digital tools were used for the manufacturing engineer to design this solution virtually. Okay, so the manufacturing engineer basically defined the disassembly of the product and the assembly into a module and the packaging within a container. So here's another example of operation simulation being done in the virtual environment for boom welding line. Okay, what you see here is a boom, a loader boom. So the loader boom, it's a combination of manual and robotic process. So using digital tools and using the virtual environment, we were able to simulate the entire operations, right from input to the output, to match the demand for this particular weldment, which is used for the boom assembly. So here the key was to generate the operation sequence and to simulate the entire operation, including this involved manual welding, at the same time robot welding. So you can see robots in the line. So here the robots offline programs were developed, and also the manual welding was simulated. At the design stage itself, the reach of the operator for the respective weldments were validated, and the entire operation was simulated to meet the demand output of the line. So this is actually just a pictorial representation of how the overall virtual manufacturing scheme of things come into place. Right from, it's very hard to read here, but this is the best I could do with the screen, right from defining the product process flow diagram into developing the line design and doing the operator ergonomics, doing the tooling designs, doing the product shipping configurations, and also doing offline robot programming for welding, and also offline inspection programs for the coordinate measuring machines. So this is what a manufacturing engineer today goes through in his routine job when he works on new product development life cycle in the industry. Okay, so now we'll actually end the session with a video, which is actually a commonly available video on the internet, but it demonstrates the ability to, or the real-time situation where virtual reality is used today for various applications in the product development lifecycle. Again, this is a video that is available on the public domain, so anybody can go.
Being able to physically get your hands on a tractor without physically getting your hands on a tractor is very important, in my opinion.
This technology allows us to visualize tractors earlier in our design process, so we can shorten the time from concept to production.
Tractor platform customer support engineers are using different visualization tools to view three-dimensional models prior to any physical builds.
We used ICID software paired with an HTC Vive headset. And this combination of hardware and software allows us to open a complete tractor, 15,000 plus components.
It's just like being there on a tractor.
Participants can take apart a tractor, disassemble, cross-section tractors in real time.
Probably one of the neatest things that I've ever done was, for the first time, I actually put on a headset and rolled around on the floor pretending that I was working on the tractor, where just 2 years ago, I was actually doing that on a shop floor, but this time I wasn't actually getting dirty.
So we like to use Creo View and visualization to see how we have access to different components on the vehicle. We use virtual tools when we can't come to a solution using traditional 2D models.
Usually we find issues with tooling or design or facility layout.
We show them 3D models as well as the virtual environment to get a better understanding of how we can better influence our tractor design. It saves a lot of time and money being able to virtually evaluate it before you build hard parts.
This technology makes my job easier because the engineers are working with their own geometry in a natural way. But we use many tools to design tractors, and this is just another one.
Okay. Okay, so those are some of my colleagues during my earlier job, but this is what today a manufacturing engineer sitting in a technology center virtual environment works on in reality. So that brings an end to my presentation today. And Mr. Umar, if you want, we can go into the question answer sessions.
Okay, sir, you can go to question and answer. Sir, you can go to question session, sir.
Yeah.
Some question I have
Okay,
mailed.
so I will go into the question session just a second. Just give me a second. Let me open the question list that you sent me. Okay, so I will open the questions document. Can you see my screen?
No, sir.
Yes, sir. Yes, sir. We can see. We can.
Oh, yeah, now, yeah.
So there are many questions. So I'll probably do about 10 questions in the paucity of time. So one was, what is the difference between virtual manufacturing and digital manufacturing? Okay. So I think we have now covered that topic. Yesterday we did digital manufacturing, where the use of digital tools to aid the manufacturing function. Now so digital manufacturing is actually a subset of virtual manufacturing. Virtual manufacturing does not necessarily mean you use digital tools. You sit at an offsite center, use a computer and support manufacturing activities. And digital manufacturing enables the performance of virtual manufacturing function. So that's the relationship between the two. The other question that we had was, what is the future scope in this area for aerospace engineering students? So obviously aerospace is much advanced in its design and manufacture compared to the automobile and other fields. So there will be a lot of scope. The virtual manufacturing and digital manufacturing in the aerospace domain is much more matured. So when a student gets into that domain as a designer, as a manufacturing engineer, it would be much more challenging and they would have much more scope in this field. Okay? Because their virtual validation, virtual engineering is very, very critical given the cost and the size of the product. The next question we had was virtual manufacturing in the context of industrial engineering. So again, industrial engineering is one of the fundamental things which is still used in every company for deriving its manufacturing processes. Because industrial engineering talks about the overall time it takes to manufacture a product. So it talks about how it is estimated, what are the governing functions, etc., which is very important today. As we saw during the presentation also, it is one of the key elements of manufacturing engineering function. And it is today possible to use virtual tools. There are standard libraries, there are standard tools available. So one doesn't have to go to the shop and physically do a time study. He's able to sit off-site and still do time study estimations using the animations and using the standard data. Third question I have is, how can the conventional manufacturing industry move forward with the disruptive digital manufacturing design for 3D topology station, etc. I think this will only be demand based. Okay, like we saw with the COVID scenario, how companies which were not at all involved in making protective personal equipment have started making them. They started making glasses, they started making face masks, they started making ventilators. So I think it's only the demand that would define it, because only when there is a demand, there is going to be a cost sense towards usage of this. But having said that, I think for companies to compete in the global market, it will be essential for them to embrace this technology slowly but steadily. Applications of virtual manufacturing, I think we have covered most of it. One of the main intent of me showing some examples from the Indian products today, from what we see in a day-to-day life, was to explain the application of virtual manufacturing. We saw it in a bogie design, we saw it in the press shop, we saw it in how parts are shipped, etc. So obviously, applications would have been evident from today's session. Any good software used for virtual manufacturing? Yes, I think yesterday we had covered this. For those who are not participated yesterday, there are many commercial softwares available, such as Dassault System has its software. Siemens is a market leader in the PM softwares, and we have Creo toolset which is available. So there are many softwares that are available for enabling virtual manufacturing function. Then advancement in virtual manufacturing. Obviously, there's a lot of advancement, in my opinion, that still needs to happen, because we are at the periphery. We are where we see applications. I remember examples of doing ergonomic studies where it would take 20 days to simulate the actual environment, which with virtual reality today, we are able to do it live, as we saw in the last video. You don't need to spend that 20 days. You probably need to spend 2 days to prepare a model. And now with further technologies coming in, I think this is only bound to become better. So there's a lot of opportunities and advancement in this field with AI, artificial intelligence, and machine learning focus coming into the manufacturing industry. So I think that's the questions we had specific to virtual manufacturing. Anything else you wanted me to cover, Mr. Umar? Otherwise, I think we are done for the session.
No, sir. Very thank you.
Thank you, sir. Shall I conclude, sir?
Thank you, sir. Thank you, sir.
Shall I conclude?
Yeah, it's conclude.
Sir, am I audible?
Yes, yes.
Shall I conclude?
Yes, yes.
Okay. So, good evening, everyone. It's a good time to propose vote of thanks. It's a really honor to me to propose vote of thanks. So, first of all, I would like to thank the resource person of this webinar. Special thanks to Rohit Malaya sir and then Mr. Pratik Navalpattam sir for their excellent and informative webinar. So, the session is really meaningful, and we learned how virtual manufacturing happens in industries. So thank you very much, sir, for your continuous support, and we will get back to you, sir. We will continue in some other way. Thank you, sir. And I would like to thank my TCE, so TCE management, as well as our respected principal, Dr. B. Abhay Kumar, sir, to allow us to continue this kind of webinar. Thank you, sir. I'm extremely grateful to our beloved head of department, Dr. K. Chakolimi, sir, for his continuous support and guidance. Thank you, sir. I express my sincere thanks to Mr. J. Umar Mohammed, sir, Ashwin Pova, sir. So he is one of the organizers of this webinar. Thank you, sir. I also like to thank faculty of mechanical engineering and then students of mechanical engineering. Thank you all. So finally, I would like to thank all the participants from various institutions and my own TCE for your active participation and involvement. Thank you all, and we will meet again for these different webinars. So stay safe and be happy. Thank you all. Thank you all. Thank you, sir.
Thank you, sir. Dear participant,
Thank
we
you, sir.
have
Thank you.
given the feedback link in the YouTube chat box. Sir. Please fill the chat box link in the YouTube chat box. Thank you, sir. Thank you for your wonderful webinar, sir.